In the very first section, you saw that in functional programming we use recursion instead of writing loops. We relied on recursion throughout the whole course, so by the time you reach this section, you should already have a good idea of what recursion is and how it works. We will start with a gentle introduction of recursion, followed by a comparison of recursive and iterative solutions. Remember, for every recursive solution, there exists an iterative solution. We will continue with the introduction of accumulator variables and use them to introduce tail call optimization, an important optimization technique that makes recursion a good alternative for loops. In the final part of this section, we will introduce another optimization technique, memoization. Let's start with the first topic before moving on to learn some optimization techniques. First, you will learn what recursion is in mathematics and in software development. You will also find out about different types of recursion. At the end of this section, you will see how to transfer iterative solutions to recursive solutions by using accumulator variables. In mathematics, a recursive definition defines a concept in terms of itself. For instance, the definition of factorial is that 0 factorial is 1 and n factorial is n times n minus 1 factorial. Notice that in the recursive definition, there is always a terminal condition. If there was no terminal condition, the recursive definition would never end, just like an infinite loop with no exit condition. In software development, a recursive function is a function that calls itself. Recall the factorial function from section 1. The function reads like its mathematical definition, and it also contains a terminal condition. Recursion in functional programming is a tool to perform looping. Compare the two solutions on screen. You can identify the same elements. Instead of loops, we use recursive function calls. The terminal condition num less than or equals to 1 terminates recursion. At the same time, the negated condition num greater than 1 keeps the while loop running. Efficiency-wise, the iterative solution tends to be better because for each function application, a new stack frame is created in memory, and after a fixed limit, a stack overflow error is thrown. The problem doesn't occur in case of the iterative solution because it just allocates space for just a couple of variables. When it comes to the different types of recursion, they can either be single or multiple. We are talking about single recursion when a function refers to itself once. For instance, factorial is created using single recursion, as factorial calls itself once. If you are interested in an example for multiple recursion, consider an example summing the values of a binary tree. In the implementation, our terminal condition is that a null tree has a value of 0. If our tree is not null, we return the sum of the node value, the sum of nodes in the left branch, and the sum of nodes in the right branch. This is multiple recursion because some elements is called more than once inside the function body. Another dimension for classifying recursion is whether we use direct or indirect recursion. All our examples have been direct so far, as our functions directly called themselves. In case of indirect recursion, the function doesn't directly call itself, but rather calls another function that eventually calls the original function either directly or indirectly. We will not deal with indirect recursion in this course. Let's get back to the SumElements function for a moment. A generic rule is that every recursive function can be implemented in an iterative way, and iterative solutions can also be expressed recursively. Most software developers come from an imperative background, therefore it is good to exercise the skills of traversing back and forth between recursive and iterative solutions. In fact, as we targeted mostly functional programming in this course, instead of pure functional programming, sometimes it makes perfect sense to implement some of our lower level functions iteratively to optimize performance. This is exactly what underscore and lodash does, for instance, even with some of its higher order functions such as map, reuse and filter. Let's rewrite the SumElements function in an iterative way. Remember, we're not allowed to call iterative SumElements inside the function body. Where should we start? It is evident that we should initialize a sum of nodes variable to 0 and return its final value at the end of the function. You may feel puzzled at the moment, not knowing what to write inside the function body. Whenever you identify this feeling, recall a trick that will frequently help you transform your solution from recursive to iterative. This trick is the definition of an accumulator variable. Accumulator variables accumulate the state space traversed by recursive function applications. In this case, our accumulator variable is going to be an array consisting of the nodes we have not traversed yet. We will initialize this accumulator to an array containing 3. With the accumulator variable, everything falls into its place. While the list of nodes is non-empty, we will pop a node from the list. If our node is not a null node, we will add its value to the sum and push both of its children to the accumulator array. Let's test the iterative function. You can see that it yields the same result as the recursive solution. We will revisit the concept of accumulator variables in the next video. We have now covered what recursion is both in mathematics and in software development. You have seen that there are different types of recursion available to you, and you have also learned a trick enabling you to write an iterative solution instead of a recursive solution.